Yeah.
You use the KNK tables for your compact?
No. So again, we're operating purely from the audio signal here. We're restricting ourselves to the audio signal. And so we had to create a mapping from the periodicity pitch images to the chroma vectors. So what we did is we took a really broad corpus of melodies, chord progressions, things where we knew clearly had the answer, and we just trained a back propagation network, or trained a weight matrix using back propagation between the periodicity image and what we'd expect to see on the chroma vector. Use that to train a weight matrix, and we did so successfully. I mean, compared to sort of MIR standards, we were classifying 85, 90% accuracy or so in terms of the classification on the chroma vector. But then the values on the chroma vector could then still be graded. They weren't all or none. Yeah.
So this is a pretty complicated model and a pretty complicated interpretation of what's going on. And I can't help thinking about what the analog would be in visual stimulation. What belongs in a set and what doesn't belong there. And in vision, it's pretty simple. In a static image, it's pop out. You have a pattern, something is the odd man out, comes right out at you. In a sequence, which, is more analogous to a time signal in addition, picking up from a melody, the key, for example. Same thing. I mean, there's a pattern, something out of whack in the pattern in a sequence of images, it pops right out at you. And I guess I would at least think of that in vision as just kind of a reflexive response to a pattern. You've seen it a zillion times one way, and every once in a while it's different, and you reflexively respond to that for, again, I don't mean to harp on biology, but for some sort of advantageous, evolutionary reasons. Why couldn't this be pretty much as simple as that, a reflexive response to patterns that you are familiar with or unfamiliar with? And I don't necessarily mean this in enculturation in that sense, because, I mean, if the pattern is just what corresponds to what you've heard if you're talking about tones, in a harmonic series, is what I was talking about this morning. Well, that's really all you need. I mean, you don't need a lot of cognitive decision-making, complicated.
Yeah, okay, but you invoked, nonetheless, a mechanism that I think many would regard as cognitive, which you invoked the idea of a memory system, right? And having seen a pattern a gazillion times, and yes, if you're very familiar with that, then you readily get pop out.
I mean, I would put that in terms of, it's memory, but memory has two varieties, evolutionary species memory and individual learned memories. And I think, again, we were talking a little bit about this before, I mean, you don't really have to go one way or the other in that and make it complicated. I mean, you can view it just as the species has always been inclined to recognize tones as human expressions of vocalization. It's there. You don't need to complexify it.
Yeah, I'm not sure though that you would still get all the results that you do get in this literature, which is if you just present a partial prime, do you activate that full schema? So if I just play you a single note on the piano, you're going to be likely to hear that as the tonic, okay? And so that's going to now activate this expectancy profile for all these other notes. And I'm not sure that you get, there's a simpler mechanism to be invoked that would generate all that based on that sort of impoverished signal.
It's kind of like a sequence of images. I mean, the first image, imagine frames of the movie, and 50 of them or something. The first one sets the pattern for the second one, and the second one for the third one, and everything should be, in a scene moving in some kind of frequently experienced relationship. And I don't really see why there has to be a difference. One note, one frame, it begins to set a context.
Sure, absolutely, and you know, and I think that, I mean, it's largely encapsulates the big debate here, and it's the question is the context that accumulates in sensory memory sufficient to drive your expectations, or is that insufficient? You know, do you need to tap into some other sort of memory trace that can help inform the expectation? And you know, I think what these results are showing, it's actually a combination. You know, you just accumulating that sensory information to generate the predictions isn't quite enough. I forgot to mention there are actually some really nice studies from Oram and Cuddy in the mid-90s, and then more recently from Psyche Louie, which asks the question, what if you expose somebody to a system where you now skew the statistics? If you move the statistics away from Western tonal music, and you expose a listener to this new statistical distribution, will they now make their goodness of fit judgments in accordance with that new probability distribution? And what you find that in fact people do shift. People do start making, you know, basing their judgments in part on those new distributions, suggesting that they're very quickly learning kind of what you're suggesting, right? You're seeing this regularity over the short term. Now something doesn't fit in, so you readily perceive that. But it turns out even in certainly the Oram and Cuddy, you need both components. You can only explain the data in part by the newly learned statistics, but then part of that's also being still driven by this notion of a tonal hierarchy and long-term memory. Finn?
So a common challenge to key finding is modulation.
Mm-hmm.
And I was wondering if how your model, then you have examples, you can think of examples of how your model is handling modulation in songs, considering we're dealing with real songs, and how that gets regulated, whether you might have a clue as to is this time for the top down to get involved, or you know, is there an error for a while, or how does that?
Yeah, that's a very good question, and so two comments on that. One is I'm not claiming to have a model of key finding. Any sort of simple, that's not my goal. I'm not trying to do that. And, okay, you could call that a cop-out, and in part it is, okay? But the other point I want to mention, and this is maybe some of you appreciated this when you saw those animations, is that sometimes you sort of get that, you know, you'll have your focus and then it starts spreading, right? And so I think that what the model this type of model captures, that the symbolic models just simply cannot capture, are these implications, those subtleties of now this other region of tonal space is being implied, you know, then it jumps over there. And that's very, very difficult to capture, I think, rigorously. You know, people talk about this key, you know, we're in this key and now this key is being implied, and so then you can do your functional analysis in the original key context or in the new key context. But I don't think that captures the subtleties that this model captures. So it's somewhere in between sort of rigorous key finding and saying, look, let's use this model now as a basis. You know, we think this is a reasonable model. It's based on psychological data. It explains psychological data. Therefore, the torus is a reasonable model. Okay, and so now the next goal is to actually relate this to meaningful experiences. So while this plays. This is an animation of a melody that we composed that systematically moved through all 24 major and minor keys over the course of 7 minutes and 40 seconds. So basically spent 20 seconds in each key. And the goal here was to use this melody, you know, basically put people in an MRI scanner and have them perform two different types of tasks, either tonal pop-out detection or a timbre deviance task, while they listen to this over and over. So 4 times within a scanning session, and then 3 separate scanning sessions on different days to try to identify, are there parts of the brain that are now following this pattern of movement in tonal space? Okay? So that was the first minute, so first 3 keys of this modulating melody, and so you can see them moved around. All right. Brief comment about neuroimaging methods. It's not, what you're measuring is not directly the activity of neurons, but rather it's an indirect measure of neuronal activity. You're measuring the blood oxygen level dependent signal, which is associated with the fine regulation of the blood supply to all these different locations in the brain to deliver oxygen and glucose to active regions. And basically what you do is you measure that signal, just schematized here for one little point in the brain or one voxel. And then the name of the game is to correlate a model of either the task or the stimulus or the subject responses, some aspect of the subject's experience with that signal. And if it's correlated and you do all your statistics and everything, then you start putting these little colored blobs on the brain. So that's the fMRI in a nutshell. Okay, so to do this for the toroidal model, what you can do, so you all saw these animations, music moving on tonal space. So basically this pattern is changing through time. And what we need is a description of that pattern that has fewer variables than all the many different points here. And so what you can do is just do frequency analysis, spatial frequency analysis on the surface of a torus. Here's the mathematical formula for this, and you're just estimating each of these coefficients. It's most easily, I think, appreciated with this slide, where what you're doing is you're taking one of these harmonics, one of these spherical, toroidal harmonic components, and you're now multiply it by this coefficient. And this is the cumulative sum here. So to get this original activation pattern, you can express it as the weighted sum of these spherical harmonics here. And you get this pattern. You have some other pattern at a different moment in time, and so that is a different that's a different weighted sum. So basically, you have each of these individual regressors and their time-varying coefficients, and you can ask how well does each regressor correlate with the bold signal, and then as a group, you have to treat them as a group. You ask, do they explain a significant proportion of the variance? Okay. So while I'm hopefully getting my power cord, which I hopefully didn't really know. Does anybody have a Mac? I got one. I'll get it. Thanks.
It's right under the table. There's a there's another one.
It's just sort of the brief summary slide from this. What was the consistent result? So even though for individual subjects now you could find various parts of the brain that were showing the sensitivity to movement in tonal space, what the most consistent result was that this region here, the medial prefrontal cortex, across sessions within individual subjects and for all subjects, exhibited this tonality tracking behavior. And what's illustrated here is just the sensitivity on a particular session in a particular subject of a particular point in the brain to a particular region of tonal space. Okay, but this was a little bit of a puzzle. Why the medial prefrontal cortex? Why was that showing this activity? And this was done in the early 2000s when there was less known about the functions of the medial prefrontal cortex, other than that it's implicated in emotional processing. We're coming off the rails here. But it hatched this idea that perhaps music memories and emotions might be linked in the medial prefrontal cortex. And the reason I got to thinking this was because I was at Dartmouth, and at that time, a colleague, Bill Kelly, had just published a paper showing that the medial prefrontal cortex becomes more active when people make judgments about stimuli in terms of how relevant is that stimulus, or how well does that describe me as a person. So when people are making these self-referential judgments, that tends to drive the medial prefrontal cortex. And so there's this beginning of this literature showing that the medial prefrontal cortex is really important for these self-referential memories and also emotions. And so I was thinking about, well, okay, you know, we've been modeling music cognition, all that stuff is great, but at the end of the day, we need to relate music, the music we listen to all these experiences that we have with music. And again, we have this dynamic structure, and if the medial prefrontal cortex is somehow tracking that dynamic structure of music, which is essentially serving as a soundtrack for our experiences with the music, then maybe this is a place where the retrieval cue, music, might be interacting with all those components of memories or, say, ongoing thoughts that we're having with the music. And so that led to this idea here, now just some more recent meta-analyses looking at the functions of the medial prefrontal cortex. So indeed, when you're thinking about traits of others, close others, or self-referential judgments, all these types of tasks activate the medial prefrontal cortex, as do emotional judgments, things like that. Here's an analysis of emotion papers that tries to distinguish sort of subnetworks of emotion processing, and here the medial prefrontal cortex is actually a core location within this broader emotion processing network. Okay, so music evoked autobiographical memories. All right, can we actually evoke these in the laboratory? So, you know, the challenge here is that these are going to be really idiosyncratic for different people, right? Something that evokes a memory for you, you know, another person might have absolutely no association with that song, even if they've heard it before. They might be familiar with it, but it may not trigger a memory. So a strategy that we hit on was to take just these 30-second excerpts from Billboard Pop and R&B charts, excerpts chosen randomly from a period when the subject was 7 to 19 years old. We just use those excerpts that you can get as previews from the iTunes store. And then subjects rate them on familiarity, how memory evoking are they, so autobiographical salience, how pleasing did they find the excerpt. And then those that they label as weakly or strongly autobiographical are followed up with several forms and open-ended response options to try to get at the memory content. So did it remind you of a specific event, person, or period in your life? Does it have emotions associated with it? How strongly did you experience these emotions in the moment? And then subjects provide written descriptions. So using this strategy, on average, half of the songs are familiar, and of those that are familiar, about half evoke some sort of autobiographical memory. So it actually works pretty well and gives us different categories of response to these pieces of music. Generally, people experience these songs as pleasing. They agree that the songs often evoke emotions, and actually that those emotions are experienced somewhat or fairly strongly in the moment. So we believe we're actually helping induce an emotional experience. Some of these memories are, so here's just a few examples. Some are kind of detailed. This is, first one's just more general one, kind of a lifetime period. This was a popular song during the summer when I was in the 4th or 5th grade. It just reminded me of the park where I spent most of my summer. So it's kind of a vague memory. Others are very specific, such as this one. The person was reminded of a friend from high school in the car at a specific intersection of Diablo Boulevard and Novato Boulevard in Novato, California, waiting at a red light. And thanks to Google Maps, we image of the intersection, the red light and all right there. So it's with all, anyway, next goal actually is with all these recent advances in decoding images, visual images based on fMRI data. Next goal is to actually try to do that in response to music evoked autobiographical memories. Now what's kind of cool is that some of these songs tell stories. You can start to piece together a person's biography. My apologies again to those of you who have seen this slide several times. So this is one subject describing periods of her life. In response to this song, simply I was in junior high. And then this song comes up, Heaven. I was not quite 18 yet. My boyfriend